right. And then last question, has anybody heard of Swift or has used Swift? All right, we're cooking now. Okay, so I'm Andrew. Today I work at Vercel. Has anybody heard of Vercel? All the same people, great. So I'm a software engineer at Vercel. I work on their CDN and edge network team. Most recently responsible for their security offerings, which don't exist. So we are actively building them. And 6 years ago, I started at Barstool Sports, and I was there through the sale that happened last year. And the unique thing about Barstool is we were probably the first org of that size to use serverless, specifically Lambda. And we were using it back in 2017, it was 90% of our infrastructure. By the time I left, it was 100% of our infrastructure. So we were very, very early to the serverless space. And before Barstool, I was largely an iOS developer. So I built quite a few different iOS apps. Big fan of Swift, used to be a fan of Objective-C. And so my goal was always to bring Swift to the back end, which is what I have a lot of experience in these days. And so we will get into that, right? So why should we be using Swift on the back end? So it's a general purpose language, but it is compiled. It's extremely type safe. And Apple will tell you it's very powerful for newcomers. I think that's up for debate. It's also extremely complex in a lot of ways. But more importantly, it's incredibly fast. You know, you're getting the same performance as something like C++ or Rust or Go. And it's just way safer than something like Go. It's nearly as safe as Rust, not quite at that level, but it's just a magnitude easier to use than Rust. So for that reason, I think it has a lot of application on backend servers. And because it's safe, it's now White House approved. I don't know if you guys saw that, but we're moving towards memory safe languages. That is a big deal. So yeah, why Swift on the server? Couple of things I just said. Incredibly low memory footprint. I'm sure you've all heard of garbage collecting. So Swift does not use garbage collecting. And this is a big deal for a lot of reasons, but one of the biggest ones is there basically no CPU contention with something like automatic reference counting. You know, as a programmer, exactly when memory is released. Whereas with garbage collecting, you actually have no idea. You're just kind of relying on optimizations that the garbage collector is doing for you. And when you're doing things like thousands of requests per second, that garbage collector can start to create really weird CPU contention. So Rust gets rid of this entirely. They basically don't even have a heap. Swift is kind of like this in-between state of something like Rust and Java, where it's still very predictable when memory is cleaned up. And this is a huge deal for servers. The next big thing is concurrency. So has anybody here used Go or familiar with Go? Yeah, so Go, you could basically deadlock yourself within 5 minutes of using it. It actually makes no sense to me. You use something like channels or whatever, and if you're a newcomer to Go, like you're basically guaranteed to deadlock the first time you learn to use it. In Swift, those are just compile errors. It's actually really hard to deadlock when you have like concurrent code. And that is super useful for servers with many cores, many threads, things like that. Other things that we'll get into, really fast startup times. Anytime you're building for the platform you're deploying on, like Amazon Analytics or whatever, you're basically guaranteed to start up a lot faster. You take something like Node, just-in-time language, you lose a lot of those guarantees. So Node is like a magnitude slower to start up than something like Go or Swift. And then the other big thing is huge ecosystem from iOS. So any HTTP client that works on iOS, you get to use on the back end as well. So you basically get the advantage of, you know, similar to NPM, you have this huge ecosystem of stuff that you can use for Swift. So the next interesting question is why serverless? Is anybody here deployed to Lambda or use similar services? Yeah, a couple of you. So what I would say, so serverless is really interesting to me because I think a lot of people think of it as a compute model. And I would say that's a completely wrong way to think about it. Like serverless is a billing model more than anything else, right? And providers like Amazon and Google, serverless came to be because they have these massive warehouses. They have all this extra capacity. And how do they sell that extra capacity to you? Serverless was their answer. And it's very much a billing model. And that's really important for the rest of this talk, is just keep that in mind. What I also think is interesting about serverless is they kind of made it a deployment model. You might be familiar with deploying, you know, something like Docker to Kubernetes cluster, something like that. Serverless gets rid of a lot of those things. They put more guardrails up, but they give you this ability to deploy something like super consistent and scale a lot easier. So you're just uploading like a zip package, for example, as opposed to building some huge like Docker container. And then the next thing we'll get into is the scaling model, which is pretty related to the billing model. You can deploy a lot of things for free, and then as soon as traffic comes in, it'll scale up and then it'll scale right back down. And the scaling model, I would say, is more of a side effect of the billing model. I wouldn't think that just because somebody calls something serverless that it can scale to infinity. I think that's a terrible way to think about it. But in a lot of cases, this is what they're trying to pitch, right? All right, so for this talk, we are going to deploy 5 apps. There is a lot of code, so you're gonna have to bear with me, but we're gonna deploy 5 different things. So we're gonna deploy Swift Node and Go on ECS, which is Elastic Container Service. So this is like, think of this as Amazon's version of Kubernetes. And we're gonna benchmark all 3 of them so you can see what that looks like. And then what I want to do is deploy specifically Swift to AWS Lambda, which is Amazon's serverless functions product. And then we're also going to deploy Swift to Vercel because I work there. So that's how I get to do this stuff. So here's the setup. I have a proxy at this URL, and each of these paths is going to invoke these apps, right? So /ECS Swift is going to hit a container running Swift on ECS. Same thing for Node, same thing for Go. Lambda is going to hit a Swift Lambda, and /Vercel is going to hit a Vercel endpoint. So all the benchmarks are going to run through this proxy. Very important to remember this, so keep this in mind. All right, so here's what we're going to deploy. A little hard to see this code, but this is what a Swift HTTP server looks like. Has anybody seen like a Node server or Go server? Hopefully this actually doesn't look too different than what those look like, right? You have a router, you probably see .get/star, .post, whatever, right? If any Express people here, like it actually looks fairly familiar. You listen on some address and a port, and you start the server. And so any Node server or Go server is like nearly this many lines of code. It's really not very different. You get all the fancy language features. You'll see try awaits in there and things like that. So this is like the exact code that I'll be deploying to ECS. And this is the architecture that we're going to have on ECS. So we have an internet gateway because we have to get traffic from somewhere. We have a public subnet, which is basically where the traffic enters. And this is completely open to the internet, so we don't have any guardrails there. The main guardrails, we're only listening on port 443, so we're just accepting HTTPS traffic. And this is what's called an application load balancer. And keep in mind too, this is the non-serverless model. These are all the things you have to do when you're not doing serverless, right? So these are the complex things, right? So we're gonna have an application load balancer. That load balancer is gonna talk to a private subnet. So this is now protected. It's completely protected from the private internet. And the only thing it's going to accept is HTTP traffic from the load balancer. Inside that private subnet, we will have Swift containers that can accept traffic. And so the goal here is like, what does it take to actually deploy this? And what does this cost? And this is a very hard thing to figure out. And that is like the main purpose of this talk is how can we beat this diagram as people building startups and things like that, right? So let's get into it. I'm going to use Pulumi. Has anybody heard of Pulumi? Awesome. So Pulumi is a TypeScript, or actually they have a few different languages, but for this talk, we're talking TypeScript provider on top of Terraform. So they're going to wrap a lot of those primitives I just talked about, and they're going to make it just slightly easier to deploy those things. And let's get into it. So step 1, we need a VPC. This is an Amazon primitive. It basically says this is our private network, and we're going to keep everything in this VPC. Step 2, well, we're doing containers, so we're going to deploy Docker. That means we need an image repository. And so we're going to create one of those. Not too bad. Step 3, now we have to create a Docker image. This Docker image gets to be stored in that repository, which the containers will pull from. A few more lines, but not terrible. I have an M1 Mac here, so we're going to be building for ARM64. That is a nice feature. This is what the Docker file looks like. I will say, so this is a Swift example. It's actually pretty clean compared to a lot of Docker files I've seen. So to quickly walk through it, we're going to build on an Amazon Linux container. Really nice thing that Apple does is they actually provide Docker images for all of the big OSs, Amazon included. So we're going to build directly for Amazon Linux. We have a single build command, and then we're just going to we'll basically copy over the final build product, and that's the thing that we're going to be running. So this is actually pretty good. Could be a lot worse. Okay, step 4, we now need what's called a cluster because we have a bunch of nodes that are going to live inside of this cluster. So, okay, fine. Not so bad. And here's where it gets a little bit ugly. Now we need these things called security groups because this controls where the networking comes from, right? What data do we want to allow in and what can we send back out? In this case, for the load, this is actually for the load balancer. We want to accept everything, right? So I'm just saying all traffic, any port, any CIDR, it doesn't matter. Now we need another security group because remember we have our private subnet. And the only thing that this is going to allow is traffic from the load balancer. And you can see that here. If you look for this security groups array, we're passing in the thing that we just created. All right, step 7, here's our load balancer. Now we have to do HTTPS, right? You can't deploy HTTP these days. So we have some long certificate that we have referenced here. We're going to be listening on port 443. And we also need what's called a target group. Now our ECS container has to listen on some port that is not 443 or 80. So in this case, we're going with the classic 3000. And of course, you need a health check. Whew. Step 8, now we're on the task definitions. So this is the thing that describes how your instance runs. So I am requesting here 4 cores, 8 gigs of RAM. We're going to run an ARM64 again, because I'm building on an M1 Mac. And we do some port mapping stuff. There's also environment variables here and other things like that. Step 9, now you have to put it all into what's called a service. I have no idea why this exists, but it does. So all these things get plugged into this. And finally, step 10, now you have a URL that you can share with all your friends. So you have 10 steps to try and deploy a 10-line HTTP server to AWS. And you call Pulumi up. 27 minutes later, you will have a hello Swift or whatever you deployed URL that works in your browser. So this is the non-serverless model. A ton of steps. There's nothing auto-scaling here. There's no metrics. There's no alarms. There's nothing, right? Like that is like, those 10 steps are the bare bones it takes to put an HTTP server in AWS correctly, I will say. You could probably do it in a lot of other ways, but I think that diagram of like public and private subnets should be at a minimum what you deploy today. If you're not doing that, you're doing it wrong. So that to me is like the minimum that it takes to put a server online. The cool thing is though, I will say, so we're deploying Node, Swift, and Go. All those steps I just showed you, just throw that in a for loop. And I'm just passing in Node, Swift, and Go. And I basically just have 3 Docker files, 1 for Node, 1 for Swift, 1 for Go. And this is actually pretty neat. And like props to Pulumi for this. Just by putting this in for loop and I call Pulumi up, it'll actually deploy all 3 of those stacks. And that's actually pretty cool. Like I'm a big fan of something like that. Okay, we're at Vantage, so we have to talk costs. So this setup here, we haven't even hit a request yet. We're at $93 a month, right? And just think like, this is just for prod or for dev or whatever. If you want a preview URL, or if you want to duplicate the stack, if you want to go multi-region, anything else, just keep multiplying that $93 a month for a 4-core server with 8 gigs of RAM. And that to me is I think a major blocker for new companies and especially startups. All right, so let's benchmark this thing. So we're going to start with 1,000 requests per second. Anybody here have a startup doing 1,000 requests per second?
Under DDoS.
Under DDoS, exactly. Okay, great. So we're starting with a high bar. Let's start with 1,000 requests per second for this benchmark. Node does pretty well. So we're looking at an average of like 15 milliseconds at 1,000 requests per second, and we're sustaining that over 60 seconds. So good job, Node. Go, same thing. A little bit lower, you got like 12 milliseconds, makes sense, compiled language. And Swift, same deal, we're at 11 milliseconds, but right in line with Go, which is what you would expect. Okay, let's bump that up. Let's go to 2,500 requests per second. And let's see how we do. So Node takes a bit of a dive here. And remember, this is just a single server. And so anybody familiar with Node, we're not running cluster or multi-process. So Node is literally single threaded. And so it actually isn't even taking advantage of all 4 cores in this case. And you can see here, it does okay for about 35 seconds-ish and then kind of falls off the wagon. Go, on the other hand, is very multi-threaded and basically keeps the exact same performance profile. So that looks great. And Swift, extremely multi-threaded as well, keeps the exact same performance profile. So pretty good. Good job for compiled languages. This is why we use compiled languages on the back end. Although I will say I do love Node, but for performance reasons, compiled languages make a lot of sense. So let's see if we can stress test these. We're now going to go up to 5,000 requests per second, and nobody's at 1,000. So I guess this is kind of like overkill, but I think it's worth seeing. Go kind of caps out, same deal. Let's see, what did it average out at? Yeah, about a second. Actually didn't do terrible. It did have a bit of timeouts, but similar story as Node at 5,000 requests per second on a single server, you're just going to start to hit some limits. And even Swift is going to be in the same boat. So it fared a bit better, but at the same time, you're eventually just limited by what you can do on a single container, right? And remember, in the Pulumi demo I just did, we're not auto scaling at all. We have no ability to add more containers. We can't scale up based on CPU metrics or anything. That's probably another 10 steps of Pulumi code to get to that point, right? So this is kind of our limit. The best we could do is just try and add more cores, but this is kind of where we're stuck. Okay, so now we're going to move into the serverless side of things and see how this fares. So first up is let's deploy Swift to Lambda. And this is what it looks like. So the model here is a little bit different because we're deploying to Lambda. You don't have something like a traditional HTTP server. You're not actually listening on any ports or anything like that. Lambda is providing basically your entry point, which is what we have defined here, which Swift just calls it handle. And so we have some event that comes in our case, it's an HTTP request. And we can just go ahead and respond with a response. So still pretty good, not a ton of code, and you can still get started pretty quickly here. And for this, we're not going to use Pulumi. We're going to use something called SST. Has anybody heard of SST? All right, a couple of you. So SST is what I would say is a step above Pulumi, and actually their new product actually wraps Pulumi in a lot of ways. But what they're really trying to do is give you the best practices for deploying to AWS. So all those things that I just did, they're not going to let you do it poorly. They're going to try and match what the best practices are to actually deploy a serverless application. And SST, I believe, stands for serverless stack. So let's go ahead and see what that looks like. So the very first step is we're going to create a function. In this case, so if you remember the Docker file, we're building for Amazon Linux. We're running on ARM64. And there's a step in here where I build the product to this folder called build lambda. We're going to reference that, and we're going to say, hey, we need a URL. And that's it. That's what it takes to deploy SST. So 2 steps. There's your URL. There's not, they're handling, well, actually Lambda in this case is actually handling all those different things about public subnets, private subnets, all those types of things. So 2 steps with SST. You call SST deploy, and assuming you're actually logged into AWS, you're going to go ahead and get a URL, and you're going to get it in 20 seconds, not 27 minutes. So that is a pretty big deal. And this comes down to the deployment model, again, that Serverless is kind of pitching to you. We're just uploading a package. So a deploy on Lambda is, hey, here's some zip file. Whereas a deploy on ECS is all those other steps. And that's the big difference for why something like Serverless is I think, really great. And there you go. So again, we have our proxies to the /lambda, and we have Hello Swift here. Just so you know, I'm not lying. This is the actual SST config file. This is literally all there is to it. It is literally the function and the URL, and there's nothing else here. So I'm not like hiding any details from you. It really is that simple. And this costs $0 a month. So that's pretty good, right? We don't have to pay anything. We can deploy prod, dev, preview. We can deploy, for every one of your friends. It doesn't matter. It costs $0 a month. That's amazing, right? Obviously, there's usage costs and things like that, but in terms of getting started, I'd rather take this than the $93 a month and deploy in a few seconds. So this is a huge win, I think, to move to something like this. So let's benchmark it. Yeah, go ahead.
When it was 93 per month, I think it was 4 CPUs and some of the other
8 gigs of RAM, yeah.
So do you have are you using less resources when you're using the other?
That's a great question. So it is $0 a month, no matter what resources I put in there. I think Lambda can take up to 10 gigs of RAM. And Lambda's provisioning model is a little bit different. You don't specify CPU. I think you only specify memory, and the memory gives you some allotment of CPU cores. No matter what I pick, it's still $0 a month. What changes is the usage, right? So Lambda is going to have a very different per request cost than ECS. ECS, there is no per request cost. You have to calculate it. It really depends on how efficient your code is, right? Whereas with something like Lambda, to deploy 10 gigs of RAM versus 256K of RAM is the same price. And that's actually, yeah, so that's a great question. Okay, so the benchmarks here, forget 1,000 requests per second, forget 2,500. Let's just go straight to 5,000 requests per second, and let's see what the performance profile looks like. And it doesn't break a sweat. So we're a little bit slower. So if you remember the performance profile, the other ones we were at around 15 milliseconds. So here, there's a lot more infrastructure happening. We're at about 25 milliseconds, but I could probably double or triple this before we even hit any sort of scaling limitation. And the scaling limits that we would hit are more of like AWS account configuration more than anything else. It'd be much less about your code, and it'd be a lot more about, what's your concurrency limit with AWS and different things like that. So, hopefully all of you want to be at 5,000 requests per second one day. So this is a good goal to have. All right. So last app we are going to deploy is Swift on Vercel. So let's get into that one. This is what a Swift app looks like on Vercel. I wrote this package actually before I started working at Vercel. And I really did my best to make sure that the API was as good or better than a lot of other services for deploying, or at least matching what the Vercel experience expects, but also matching what like the Node and Express folks, kind of expect. I did my best to kind of match that same thing. So you still have your router, you have, try await, you have things like .get or .post or whatever, like all that API kind of exists in here. And there's no config, there's no files, there's nothing. You just call it Vercel deploy. So we've now removed, even the steps that SST had. Vercel provides something called their build output spec, which is basically a specification for framework authors. So Next.js, Svelte, Remix, those guys, when you deploy to Vercel, you're building towards Vercel spec. And I just matched that with Swift. So behind the scenes of Vercel, it's still just Lambda. And so if you can just match their spec, if we could, we already saw we could build for Lambda. So great, if we can build for Lambda, then you can build for Vercel. It's just a matter of organizing your files in a certain way. Same deal, 20 seconds later, you'll have your hello Swift example here. Yeah, you can see here. So there's one dependency, which is this package that I built, and there's no other files, no other config files, anything like that. So we're even more towards just focusing on your application and getting rid of all these weird like infrastructure config type things. And again, we're at $0 a month. So, for hobby accounts of Vercel, you pay nothing. For pro, I think it's like $20 per user, whatever it is. But same idea, you're deploying something, you have unlimited preview URLs, and you're paying no money. And that's kind of, again, is what this serverless model I think is really about. Of course, we have to benchmark it. So we'll just go straight to 5K requests per second, and it's the exact same performance profile as Lambda because it is Lambda behind the scenes. So that's kind of what we would expect here. All right, so we've deployed all of our apps, but There is one more thing I want to talk about because I told you we deployed a proxy that was hitting all of these URLs. Well, that proxy is also built in Swift. And so that means if it was able to handle all that traffic, it should be able to handle a lot more than that. And so the proxy is actually written in Swift compiled to WebAssembly. And this is what I think is like the future of edge networking, is actually compiling to WebAssembly. Has anybody heard of WebAssembly or used it in any way? Okay, so a lot of people, I think the thing of WebAssembly is running in the browser, which is nonsense. Just forget about that. We don't need to run WebAssembly in browsers. We have JavaScript, it's great. WebAssembly is incredible at running server-side applications because of what they call their component model, where we can write stuff in different languages and it all interoperates. And that to me is like the real future of edge tech. WebAssembly in the browser, just forget that exists. And so let's talk about that. So this is the actual proxy. So the /lambda route, this is what it looks like. It's written in Swift and it's calling the Lambda URL. And if you look at this, like, this is not some like config language for the proxy. Like, this is real Swift. We have fetch requests, we have streaming, we have async wait, we have all these things. And to have an edge network that you can write in a language like Swift is incredibly powerful. If any of you are familiar with like Cloudflare or whatever it might be, you have little like page rules and you add like, oh, this path equals this, do like a redirect. Forget all that. You just want to write programming languages, and like this is the future, I think, of where edge tech is going. Pick a language that compiles to WASM, and like this is how you write proper edge code. Really similar to the others, you just call publish. In this case, we're deploying to Fastly. So Fastly's entire edge is WebAssembly. They were known as like a VCL edge, and now they've actually completely swapped, where their VCL edge is actually compiled to WASM. And they basically just provide a bunch of host calls. So things like fetching, reading responses or requests or whatever. And so all I have to do in Swift is just plug into those host calls, and we can basically have an SDK that works entirely on their platform. So forget 5 requests a second. Let's just go to 20,000 requests per second, and let's take a look at what that looks like. And 5 milliseconds. So this is a big deal, right? You can now write code that is insanely performant. 5 milliseconds, you can basically do any application you could think of at that type of latency. And that's, this is at a scale that's 20x, what we're all doing here, right? So I think there's plenty of headroom here. Another thing I want to talk about. So who here deploys with Docker regularly? All right, good number of people. So I think what's big about this serverless model is like we're no longer really deploying Docker, right? And so if you look at, I want to show you like how I actually deploy these things to Lambda and Fastly. There's no Docker files. What we're doing is we're building with Docker, right? Like I don't want to create an image that a container has to pull from to start up. What I want to do is I just want to build an executable that runs on the host operating system I'm deploying to. And so if you look at the right-hand side here, we're just building for Amazon Linux and we're calling Swift build, right? Or in the WASM example, we're building and compiling to WASM and we're just producing something. And that I think is like, this is a huge game changer when it comes to deploying. Like trying to deploy Docker everywhere, I think is a very old way of thinking. I think there's a lot of performance issues with that. You lose a lot of advantages of what these platforms are actually giving you. And I think this is a really cool model with serverless is you're just building a product and you're deploying it for whatever operating system, that provider is giving you. So then, okay, this is, I think the biggest question is like, can you use any of this stuff in production, right? It makes for good benchmarks and demos and things like that. And of course, you can, or I wouldn't be doing this talk. So at Barstool, we built our podcast network in-house. So Barstool is one of the, I think like the 4th largest podcast publisher in the US. All of that tech is built in-house. So all the streaming, all the hosting, all those things are actually built by, or were built by our team. And a big requirement was server-side ad insertion for a podcast. So when you listen to a Barstool podcast, the editors upload one file, but when you listen to it, we're going to stitch in relevant ads into that file as you listen to it. That server-side ad insertion is entirely built in Swift, deployed to Fastly. And it does a decent amount of volume, if I don't say so myself. This is what it looks like. This is like a small snippet, but you can see a lot of good things here. There's like range requests and appending streaming bodies and things like that. So, it's very much, it's giving you all the good things that Swift has to offer. And these are some stats. So, about 617 requests per second, nothing crazy, but because they're MP3 files, this is like 14 gigs a second of bandwidth. So it's a serious amount of bytes that we're serving via Swift on an edge network. So that's around nearly 3 petabytes of bandwidth a month, and over 1 billion requests a month, all in Swift. Another place to use it. So I build a side project of mine called Helios. This is an SMS marketing platform, and we use Swift for all of our real-time WebSockets. So every time you send a message and you see the UI update or you see new notifications and things like that, all of that is built in Swift, deployed to the edge. Here's like a small code snippet, but you could see if you've ever worked with WebSockets before, there's all this state management and all these weird things you have to deal with. If you have multiple containers, you're probably writing to Redis and listening to subscribers and all these things. All that just goes away, right? And in the serverless model, you're really relying on what is the provider giving me. And so in this case, we have all the primitives for things like channels and publishing and whatever. And it's just a matter, you just get to write Swift or TypeScript or whatever and take advantage of those primitives. So it ends up being really, really easy. Here's some stats. So messages, we're handling every message in, basically 5-6 milliseconds. And then another thing that we built in Swift for Helios is our link shortening service. So when you send a link, a lot of our clients send like these long links over SMS. SMS, you pay per character, so it's in our benefit to shorten them to be as short as possible. And there's other cool things we can do with that. When you shorten the links, we get like analytics, and we actually know if people open links that are in their phones and things like that. That's also built in Swift. You could see some of that here. So again, we have some router that listens on some path. We actually read these links from PlanetScale, and then we can go ahead and and redirect. And so every time you click a link in Helios, we're redirecting in 9 milliseconds. So nobody would ever. I think that's low enough, or nobody can tell. And that's it. Yeah, thank you. Thanks a lot.
All right, any questions for Andrew on anything?
Yeah, go ahead.
So with a 30-minute deploy time to ECS, isn't it a 30-minute thing because you're deploying it for the very first time?
No.
Next time you want to deploy, ALB will already be up, ECS containers will already be up. So it's just the matter of placing the containers inside as well.
No, it's actually way worse than that. So with ECS, what they're going to do is they're not going to drop a container if it has connections, right? So what's happening is like they're gonna try and drain all those connections, and they do this in a fancy way. You can basically decide when I deploy to ECS, you're going to say, hey, you have some desired number of servers. Let's call it 8. What's the max number of servers I can deploy, or I can add when you're running a deploy? So I think a common configuration is say like I'm going to say I will have 200% of my servers during a deploy. So if I have 8 servers running, what they're going to do is they're going to add 8 more servers running the latest version of my code. They're going to drain the connections on the previous 8 and start to drop them off and add new traffic to those 8. And so at a high enough request volume, like this actually takes a really long time. And so it's less about like the ALB and things like that, and it's much more like it's basically those containers running and how long it takes to run the health checks and make sure they're up and all these things, right? So that 27 minutes wasn't even the initial one. I was running all these benchmarks last night, and that was just like a random update I did, and it took 27 minutes. It's the worst. So
hot fix without that hot.
no, yeah, there's no hot fixes on ECS. Exactly, that's where feature flags come in. You feature flag everything. Vercel, we literally feature flag everything for that reason. So to deploy Vercel's edge network takes about 8 hours. So there's no hot fixes at Vercel.
Is Vercel's edge network on ECS?
No, it's EKS. So yeah, we're running EC2 basically instead of Fargate, which is what ECS is. Yeah, Vercel's edge is entirely Kubernetes. Yeah, the Vercel saying is we run Kubernetes, so you don't have to. Yeah.
What's the you mentioned WebSockets, like what's the kind of WebSockets and serverless story these days? Is that like kind of dropping well, or?
Yeah, so there's a product called Fanout, which Fastly bought, but before Fastly bought it, their whole model was we'll basically run, we'll keep connections open at the edge, right? And so every time a message comes into our edge network, we will send you an HTTP request and you can respond to it. And this is a really cool model because it basically, they also have like channels and other primitives, but what this allows is like services like Lambda, which don't have long running containers. All you have to do is accept an HTTP message. They'll hold the connection open at the edge. And now you have like this, this perfect relationship between serverless and non-serverless. Fastly bought fan out and their edge network just has it built in. And so there's basically two models. What I showed you is I'm actually handling WebSocket messages in Fastly's edge, but I don't have to. I could have specified like a Lambda origin and then they would forward it over to Lambda. So yeah, it ends up working really well. Yep.
What sort of price difference are you seeing between do you use Fargate Spot rather than dedicated EC2 instance?
Yeah, so I use Fargate Spot a lot. I mean, you're saving like 80% for something like Fargate Spot. I think the thing with Fargate Spot is you really have to understand your workload. If you're running HTTP traffic, you can never specify 100% Fargate Spot, right? Because you can't take that risk. So maybe you call it, 25% Fargate, and then you say, okay, with scaling 75% Spot. I think there's other things where Fargate Spot you can like really benefits, like Vercel's build system, for example. So when you git commit code and we build your code on Vercel, it's not Fargate Spot anymore, but it used to be for a long time. And that's like a perfect use case where like we don't have to start building your code the millisecond we get that webhook, right? We can take a couple seconds later to spin up a Spot instance that becomes available, and that's like a tremendous difference. Yeah, go ahead.
So I'm sure there's a good story, but could you tell us how you think about kind of as a disaster recovery and multi-cloud, thinking about dealing with serverless?
Yeah, I would say multi-cloud is something I basically have zero experience with, to be honest with you. I think like if you have a multi-cloud need, I'm thinking like the one startup that I think actually needs multi-cloud is like Mux. Has anybody heard of Mux, the video streaming platform? Like they actually make sense for multi-cloud, right? Like they're doing live streams, like big live streams. If you're ingesting data and you're, let's say US East 1, for example, and AWS goes down, like it makes sense for them to pay the money to try and switch over to GCP. But like, unless you're at that type of scale and dealing with like that type of real-time stuff, I think multi-cloud is a weird game to get into. I will say SST, Pulumi, they actually make multi-cloud really easy because they basically abstract those primitives. But if nobody here is doing 1,000 requests per second, stop thinking about multi-cloud.
What about disaster recovery?
Okay, so disaster recovery, yeah. So I always like to brag, like at Barstool, we didn't even have an on-call rotation because we were just so confident in serverless being able to just recover itself. And I think the cool thing is like, with ECS, like you saw in those benchmarks, how it really tails off, right? Like those containers, like they can't handle the load anymore, and they basically just start, like they'll basically just die eventually. They'll run out of memory, whatever it is. The thing with Lambda is every single request, even at 20,000 requests per second, has the exact same number of resources, right? Like there is no resource contention at all. And I think that changes the disaster recovery story quite a bit because you could actually have like incredibly memory leaky code on something like Lambda and get away with it.
Right.
I'm not saying you should, but that's just kind of the model that Lambda gives you, right? So yeah, I think it changes how you think about it a lot. Disaster recovery for me is much easier on the compute story. I think it's way harder on the database story, right? And this is where like the Planet Scales and MongoDB atlases are like CockroachDB are trying to provide a lot of value. But I think that's like way trickier to get right is recovery on the database side.
Thank you.
Yeah, go ahead.
What about runaway costs with like lambdas and stuff like that? I feel like every month I see a story about like someone who got DDoS or something like that. That happened this week with like a person where they just wake up to $100,000 bill. Whereas like let's say you have it happen with like ECS, the thing it doesn't upscale, it will fall over, which may or may not be what you want. Do you have more predictable pricing in that sense?
Yeah, it's a great question. I'm not the CEO of Vercel, so I can't answer that. Yeah, this is definitely a problem that will have to be solved. But the funny thing, hard limits, yeah, Guillermo tweeted that. Hard limits are a thing. I'm actually not a fan of hard limits. I think we need them. Like Vercel as a company needs them. I'm personally not a fan of hard limits. I'd like to see better alerting and different things like that. But it's a weird problem. And even on AWS's end, so 3 or 4 years ago, if you create an AWS account, you were allowed 1,000 concurrent lambdas, right? Just create the account and you get 1,000 lambda containers running. If you create an account today, there's some percentage chance that you have a 1 lambda container limit or a 10 lambda container limit, and that's it. And you actually have to request to get more than that. And so like that's a clear indication that like there's definitely a problem and probably more abuse than anything else that's happening with these serverless auto scaling, piece of infrastructure. I don't know what the answer is. I find it annoying that I'm limited to 10 containers and I have to pay $30 a month for AWS support to ask for 1,000, right? Like, so it's a tough problem. Not sure what the solution is yet. Yeah, go ahead.
I've done Lambda stuff forever, but wasn't there a big warm-up time issue back
Yeah. Absolutely, yeah. So the Lambda cold start story is still a hot topic, I would say. It was really bad back in 2017, 2018. So like that VPC diagram I had, there's basically 2 ways you can deploy Lambda: outside of VPC, or basically in Amazon's VPC, or your own VPC. And if you deployed it in your own VPC, you could get anywhere from like a 5-minute cold start time, just depending on whether they could spin up a network interface in time to handle some requests. So they've done a lot of like fancy computer science work. I think most of that stuff is gone, but you're still looking at, for a node application, if your node modules are large enough, it could be 1 to 2 seconds, right, to start handling a request. And so notice all those benchmarks that, we were operating in like, 15 milliseconds, right? So for 2 seconds as a cold start, it definitely hurts. And you're going to feel it the most as a startup, to be honest. Like when you have consistent traffic, like Barstool never worried about cold start times. We didn't have to. We had traffic at all times of the day. Like there was nothing to cold start. We were always running hot. But for startups, like you definitely notice it. You send out preview URLs and things like that, and things feel slow the first time you use it. So it's getting better. Compiled languages start up way faster, right? Because you're literally building for Amazon Linux, whereas things like Node and Python, whatever, they're just in time compiled, and you're going to pay that penalty. So yeah, still more work to do there. Yeah, go ahead.
What's the compile time? What's the compiled language cold start time?
For something like Swift, probably like 50 to 80 milliseconds for cold starts. Rust is like 40 milliseconds. And then, yeah, I mean, Node can be, like at Vercel, we have some people, it's like 2.5 seconds. It kills us. It's something we really want to work on. But yeah, the compiled languages are going to be substantially faster because there's really nothing. You're basically like just running, the compiled product, right? Whereas like Node, you actually have to start up Node, you have to do the just-in-time compilation, all those other things, right? All those require statements and things like that, right? Like those all take time. So yeah, I mean, 80 milliseconds is workable, right? Like that's pretty good.
You just have like a ping go into that service so it never goes cold. Is that
Oh, that's a great question. It is not a workaround, and I've seen this a lot. So the reason, so what he's asking is, let's say I have a cron job that every single minute pings a Lambda container, right? So surely that means I have a hot Lambda container. But the compute model for Lambda is they will never run 2 requests on the same container at the same time. And so what that means is if I all of a sudden get a surge of traffic, it doesn't matter that I have a hot Lambda container. If that ping is taking up compute time, that means that some other request cannot use that hot container. And so you will still incur a cold start cost even by doing that. So it's like this complete, and actually like, I don't know why nobody talks about this. Like it's a complete fallacy that these cron jobs for keeping warm containers work. They do not work. It just doesn't make sense with the compute model. But people still talk about them as if they do work. So you heard it first here. Yep.
Is that why people then have the concept of like fanning out and things like that, so you can feed it into one Lambda, then push it out so it doesn't get stuck? Is that why people do that then, or?
You know, like SQS or SNS or something like that?
Yeah, like they might have like one Lambda that like basically acts as like a gateway, which is.
Oh, like a proxy, yeah.
And then basically pushes it out to different.
Yeah,
Lambdas
so. Yeah, like I think there's this concept called like a proxy Lambda, which is like a single container handling a bunch of different requests.
Yeah.
I'm a big fan of that model. Like what I was showing you here is like a proxy model. I think, a couple of years ago, there was this idea that like every single path should be its own Lambda. And I just think the developer experience for that is just horrible. It's really hard to manage. You know, you start building your own API, you have 50 routes, and now every time you deploy, you have to deploy 50 lambdas, and it's just like pain in the ass. So I think the proxy model is actually a better model. But I think it's less about performance and more about like, it just keeps your sanity as a developer, just like deploy that. It's easier to think about. Yep.
Have you seen reduction in deployment to ECS time if you switch from rolling to Bluebeam deployments?
That's a good question. I actually don't know. Yeah, so for these, I just did that 200%. And I think the other thing with ECS too is like I noticed like Node and Go are deploying faster than Swift. So if you look at that Swift code, I had something that was like try, await, start service. And they listen for things like SIGINT and other like Linux kill signals. And I my guess is Swift, like that package I was using probably like isn't responding as fast as it should. Because there's the key with ECS is like you have to know all the signals that they send, because they send some weird ones, right? For like Fargate Spot, for example, they'll actually tell you, hey, we need this container in 2 minutes, right? And you have to shut down in 2 minutes. So like there's all these weird things you kind of have to do. And so Swift might be doing something a bit different. But yeah, I mean, even Node and Go though, when